Welcome to the Catalysts podcast. I'm your host, Patrick Morley. What if a CT scan could tell doctors not just what cancer looks like today, but how it might behave tomorrow? And what if artificial intelligence could transform those scans into a roadmap for truly personalized cancer care? These are the big questions our guest, Dr. Sarah Mattonen, a cancer researcher at the Schulich School of Medicine and Dentistry, grapples with daily. As an imaging scientist, she's a leader in radiomics, where artificial intelligence is used to uncover hidden patterns in medical images, helping doctors predict outcomes and personalize treatment like never before. From anticipating lung cancer reoccurrence to reducing side effects in head and neck cancer, her research is pushing modern cancer care into the future. So thanks so much for being with us, Sarah.
No problem. Thanks for having me.
Yeah, great. I think we'll start off with sort of unpacking the term radiomics, because it sort of will color our conversation today. Yeah. So can you sort of take me on a journey of what radiomics is and why it's so important to your research and to cancer care?
Yeah, absolutely. So radiomics is a relatively new field, I'd say, probably the last decade or so. And really what the goal of radiomics is to try to extract more information from standard medical images. So we want to take medical images that the patients are already getting as part of their cancer care journey and see what else we can find in there that the physician might not be looking at. So really what we're trying to do is extract more information from these images. Really, kind of the famous quote in the radiomics world are images are more than just pictures, they're data. So how can we extract more information from those images to use? So really what we're trying to do is pick up patterns that the physician might not see and really put numbers to those patterns. So trying to take visual representations and putting numbers to those patterns through our software that we develop. And then those features that we find can be used to predict all sorts of outcomes, specifically in cancer, whether we're diagnosing a tumor as benign versus malignant, or we're trying to predict if the cancer is going to come back. So those sort of things. So a lot of different applications in terms of how it can be used.
Right. And is it relatively new? Is there a timeline where this kind of became?
Yeah, I'd say probably early 2010s, kind of. So I'd say about 15 years it's been around, kind of kicked off, and it's really kind of gained traction with the development of more artificial intelligence applications and kind of building more complex models and that sort of thing. But I'd say, yeah, a relatively new field.
Yeah, great. Yeah. I think when you image, it's often a tumor.
Correct.
I'd imagine, right?
Yeah.
Tumors come in different shapes, sizes, textures.
Absolutely.
Is that what radiomics is going to help uncover?
Absolutely, exactly. Yeah. So we can usually take the images, and we can use any kind of images that the patient might have during their workup. It could be a CT scan, an MRI, an ultrasound. You can really apply radiomics to any imaging modality, which is great. And then you're right. We typically we contour out or kind of draw out the tumor on the images, and then we extract these features from that. So that's exactly right. They could show us differences in the shape, in the size, in the texture. Specifically, really, radiomics is focusing on those texture differences or very subtle changes in the visualization of the tumors that the physician might not be picking up with their eye.
Right. Can we contextualize this? Mm-hmm. 15 years ago, as this field sort of started to grow, what would a doctor do with a scan compared to what they do now?
Absolutely, yeah. So typically, and even still today, when we take a scan, for example, of a patient coming in with a newly diagnosed cancer, they might just be taking very, very basic measurements. So how large is the tumor? And that just might be a diameter measurement. So they might say, oh, the tumor is 5 centimeters in diameter. They might not even really look at the volume. They might look at where it's located specifically in the body or in the organ that's been affected. And then really has it spread to other regions. So it's very, very basic size measurements usually that they're all taking. They're not really looking at the appearance of what it looks like or any features even surrounding the tumor. It's just really how big is it? Where is it located? Has it spread to any other areas of the body?
Right. How long would that have taken in the past compared to where we are now?
Yeah. So typically, we have a radiologist that will look and assess these images. So it will take them quite a bit of time to scroll through all of the images because we think of these images. We have so much data there. There's kind of like each slice of the patient. We kind of put that together like almost like a loaf of bread. So it's quite a large volume of data that we have to look at. So they have to scroll through all of that, make sure that they have caught where the disease might be spread. But hopefully, as we kind of move forward with the advances in artificial intelligence and radiomics, we can kind of use some of these AI models to try to do this faster or kind of pinpoint where a physician might want to look to kind of speed up the process.
Right. Because time in cancer is of the essence, right?
Absolutely.
To save lives. How important is that?
Yeah, exactly. Because we don't want there to be any bottlenecks in terms of the workflow of the patient going through from the diagnosis to the staging to the treatment, and any delay along the way can potentially impact treatment and outcomes. So, really, anything we can do to try to speed up the workflow or help clinicians in their decision making can really have a big impact in terms of improving the speed and access to clinical care.
Yeah, right. How when you're using AI now to look at a tumor, can you estimate how many points of data you can look at compared to the olden days when they didn't have AI to do that?
Exactly. Yeah. So with AI and especially with radiomics, we can pull out thousands and thousands of features from these images. Thousands of them. Yeah. So it's not only just on, we can look at the original image, but we can apply filters, which just kind of manipulate the image in a different way and pull out more features from that. Again, that's just a different way of looking at the image. But yeah, there's thousands of features, like we mentioned, size, shape, texture, just differences in intensity that really allow us to capture quantitatively kind of what that tumor looks like. You can kind of think of it almost as like a imaging fingerprint of the tumor that you can apply all of these different featers to characterize it.
For sure. The analogies for this are quite, they're interesting. I've heard one, it's like in weather forecasting, which uses, again, AI models now these days. You can look at a cloud and you can tell if it's going to rain. Exactly. But now they can predict, where that cloud's going to go, where it's going to end up. Is it going to get more severe? Is that an apt?
Absolutely, yes. And that's exactly how we can use kind of AI in terms of the imaging workflow to kind of see what the tumor looks like, where is it going to go, how's it going to progress, and that sort of thing. So absolutely.
Yeah. Is it fair to say that this is quite a dramatic, new technology that's going to revolutionize?
Absolutely. I think kind of AI as a whole and in general is going to really revolutionize the medical imaging workflow and kind of the cancer care workflow. Just never to replace a physician or a radiologist or anything like that, but really to help kind of augment their workflow. So again, make it faster, kind of maybe point them to areas they might not have looked at, so give them something new to look at. But I really think it's going to have a big difference in terms of being able to give the best care to our cancer patients going forward.
Yeah, wonderful. We'll talk a little more, a little bit later about how that's going to work in a clinical setting. Yeah. Can you give an example of a patient who's maybe just been diagnosed with stage 1 lung cancer?
Yeah.
They get a CT scan, probably an X-ray, maybe.
Yep. Yeah.
PET scan.
PET scan, yeah.
What happens with that image? Can you take me through that process?
So as part of the general clinical workflow right now, they usually get, so diagnosis first is once they get a CT scan that they see a tumor in the lung, for example. The first thing that they'd want to do is first to do a biopsy to make sure it actually is a cancer, and it's just not a benign lesion in the lung. And then once they've confirmed that a cancer is present, then they would do a staging workup. And staging really just tells us how large the tumor is, has it spread to any other parts of the body. So really looking at the size of the tumor, has it spread to any lymph nodes, and has it spread anywhere else in the body. So to do that in lung cancer specifically, they really focus on that CT scan, which is like a 3-dimensional X-ray of the chest, and then as well as a PET scan. And the PET scan really measures the metabolic activity or how active the tumor is. So what we do for a PET scan is we inject a radioactive glucose. So things that are metabolically active or highly growing quite a bit, like a tumor, it's going to eat up all that glucose and it's going to show up as a bright spot on our image. Okay. So we use that to kind of say how bright it is, might indicate how aggressive it is. And all of this goes into forming the cancer stage, which then would be used for the physician to determine what's the best treatment for these patients.
Right. Is that a long process from
It can be, yeah. So depending on kind of timelines and availability of imaging and that sort of thing, it varies depending on availability of scan times and getting them read. And then we have multidisciplinary review boards where all the physicians get together to kind of determine, well, what is the best treatment for this patient?
Tumor boards?
Tumor boards, yes.
I think,
exactly, yeah. So it can be quite the process in terms of getting to the appropriate treatment for these patients. And really we want to kind of minimize the wait time for them as much as possible.
For sure. There's many things fascinating about radiomics and the work you do. I think one of the most interesting things or fascinating things is that with this new technology and the research you're doing, you're starting to be able to predict where a tumor is going to go, how it could spread. Is that true?
Exactly, yeah. So we've been working on over the last 5-6 years now on this early stage lung cancer specifically. So taking those CT and PET scans prior to the patients undergoing surgical resection, so where the surgeon is going to remove a portion of the lung with the tumor in it. And we're trying to predict is the cancer going to come back after surgery? So we worked with great colleagues and collaborators in the Division of Thoracic Surgery here at Western to kind of develop our databases and build our models here. And really, we've shown that we can use those radiomic features as well as other features that the patient is already getting as part of their clinical workflow. So things from the patient demographics and their clinical information that we already have as part of the workflow, and build that together to build an AI model to predict recurrence. And we've shown it is done quite well in terms of predicting outcomes, both on data sets here as well as from collaborators outside of Western as well.
Yeah, great. Yeah, we'll dig into that a little bit more in a bit. Do you tell patients this? Are you at that stage where you can confidently give a prediction, or is that...
Yeah,
I could imagine that being kind of a dodgy place to be,
exactly,
right? Because there are no guarantees, right?
Absolutely. And I think we're very in the early stages of the translational aspect of this work. But that's ideally where we'd like to go, because I think we build these models really to get them to be used in clinic. And that's the ultimate goal, is the translation aspect. So first, making sure the model works appropriately, it's been properly validated. And also kind of the next steps is first, well, how will the clinicians use our model? So will they trust the model? Will it actually change their decision in terms of management? If our model says, yes, this patient's at a very high risk of the cancer coming back, will they do additional treatments and that sort of thing? So I think we first need buy-in from the clinicians to see how they're going to use these models. And then long-term, eventually, if we can show that they're working prospectively as we look at new patients coming in, then how do we incorporate the patient into that decision-making process? So what information might they want to know about this model and how it's being used for their treatment and that sort of thing? Because I think that's going to be a big, important aspect of developing AI models in the future, especially to see how the patient fits in that, because that's kind of really the most important thing.
Right. No, absolutely. And so much of cancer treatment is odds.
Absolutely.
Right. I think that word gets thrown probably incorrectly.
Exactly.
The odds. And this technology is going to improve your ability to set those odds.
Absolutely. Exactly. Yeah. We want to be as accurate and kind of give the best outcomes possible. So, so how can we use that to kind of, give them the best chance of outcome, and also personalize medicine to give them the treatment that is going to most benefit them to get those best outcomes.
Right. Along with like sort of predicting the best to the best of your ability, you can also predict treatment.
Absolutely.
As well.
Yeah.
How does that connect to...
Yeah, so we can there's kind of different ways we can do it. We can use it to predict which might be the best treatment for these patients, whether that's surgery, chemotherapy, or radiation, kind of depending on what the anticipated outcome might be. But we can also use AI and different machine learning models to kind of predict maybe what the treatment is going to look like. So how can we plan a radiation treatment, for example, using artificial intelligence to kind of get the best treatment possible to really treat that tumor with the best treatment while avoiding some healthy tissues and minimizing side effects. So there's kind of a lot of different aspects where it can play a big role.
Yeah. Sounds like the overarching goal is this idea of personalized medicine, right? Where cancer treatment and a lot of medical treatments has kind of been one size fits all. Absolutely. Let's hope for the best. Yep. A lot of treatments in cancer especially have the harmful side effects.
Exactly. Yeah.
A lot of the work at Schulich seems to be targeting personalized medicine. How can we focus on specific cancers for a
Absolutely.
specific patient. Is that where you see the future going?
Absolutely. I agree. I think that's where the field is going. So not just with our imaging-based machine learning models and radiomics, but also incorporating other personalized medicine aspects where it's genomics, other biomarkers, that sort of thing. I think it's going to be a really holistic view and kind of multimodality approach to trying to bring all of this information, because these patients come into the clinical workflow, they have so much information that just how can we best use it? How can we combine it to really give that optimal treatment and personalized approach? Because I think that's where the field is headed.
Yeah, tailored treatment.
Absolutely.
Right? How far away do you think we are?
Oh, I don't know. That's a good question. I think we have a lot to do in terms of making sure we can build predictive models and use all of this information appropriately, and kind of see there's so much variation and heterogeneity in cancer that I think that variation is going to be always something that we have to think about, and how different patients are going to react. So I think it's going to take some time and a lot of data to kind of build these models and tools to kind of get to the point where that they're implemented regularly in clinical use.
Yeah, I think a lot of people don't understand just how research translates into a clinical setting, and there's a lot of buy-in that needs to happen from the doctors.
Absolutely.
You need funding to get the research off of the ground. Is that something that you're comfortable working in?
Yeah, it's always something we have to think about, because it's definitely, we kind of have these ideas that we come up with in collaboration with our clinician collaborators. But yeah, kind of thinking about that long-term goal, right? Like, how are we going to get it from our research lab back into the clinic? So there's so many steps along the way. You're right. It's not even just the research, it's the funding. Do we have the people power to do that? And then getting, buy-in from the clinicians, buy-in from patients, and long-term, like how best does it integrate into the workflow? Whether that's like, is it a tool? That's a standalone tool? Is it a tool we can incorporate into some system that they're already using? So much to think about in terms of how best to get these there.
Yeah, definitely. And I think in your case, and correct me if I'm wrong, it feels like buy-in from clinicians is really important when you're giving a patient a prediction.
Absolutely.
Is that, how do you navigate that? Yeah,
it's so important. And I think clinicians play such a big role in the research that we do specifically right from the beginning. So most of our project ideas come from an interaction with the clinician, either that we've been working with or somebody new that'll approach us saying, hey, we have this clinical problem. I've heard you've been doing some AI research. Like, how can we work together to kind of solve this clinical aspect? And really what we're doing all is so important and based on an unmet clinical need, and that need needs to come from the clinicians. So if they're on board right from the start in terms of developing what the research question is, kind of how we're going to formulate that research question and build our model, for example, then they kind of have buy-in from right at the beginning, and then kind of working with them throughout the process is extremely important for both me and my trainees to kind of see, kind of continuously interacting with them to see how we can get their input right up the front, right at the beginning. And then I think that carries through to how we can implement it clinically, because you're right, at the end, when it's the patient and the clinician, if they're not going to have that buy-in and want to use it, then it's really not a useful tool, which is what we want. So we kind of try to do that right from the very beginning. Yeah. And I wonder if there's not a pushback, but when you're telling a clinician, okay, we have this new tool, AI, it's powerful. Yeah. Is there a worry that, is this going to make my life more complicated? Is it going to take up more of my time? There's already burdens, as we all know, in the healthcare system. Has that come up? It has, yeah. So a lot of our studies, we try to do almost like an observer study where we kind of give the tool to the clinician just to get their feedback in terms of, is this too much time it's taking? Is it kind of a bottleneck in your workflow? Or is the information we're showing you the right information? So it's really, there's so much aspects of this to think about in terms of how they'll best use it. And I think every clinician is different too. We've gotten feedback on the same tool from different clinicians where some like some aspects, some don't. So it's really kind of how we can personalize that too to different clinicians to make it kind of a broad and generalizable tool that they'll use without too much interruption in terms of their current workflow. So what we don't want to do is add time, add another bulky thing that they need to work with or anything like that. But it's definitely interesting to always to hear different perspectives, because it's you get different perspectives depending on who you're talking to. Yeah, for sure. And I think that's what is misunderstood sometimes is that things don't just land in a clinic. Absolutely. There's a lot of behind the scenes work that goes on to that, right? There is, exactly. A lot of steps and a lot of years along the way. Definitely.
This mini-series is in support of the Allyn Taylor International Prize in Medicine.
I think this is probably a good time to maybe transition a little bit into the work that you've been doing. I think groundbreaking work. You've won an award. Maybe you could talk about that for your work with lung cancer. Can you sort of unpack a little bit of that?
So I'm really fortunate to work on this lung cancer project, really kind of since my postdoc and kind of coming to Western as a faculty member here in 2019. So it's kind of built from the ground up, and I've had a fantastic graduate student that was working on this, Dr. Jared Christie, who just recently defended his PhD last year. And really, he kind of built this tool using both the CT images, the PET images that were taken before surgery to try to predict, is the cancer going to come back after? So he's developed many different models, using both local data here as well as we've had collaborators in Seattle. So it's really nice to see kind of a very multi-institutional collaboration to see if we build something here, is it still going to work on other data? And really, he's shown that there are subtle imaging features, both in the CT and in the PET image, that predict if the cancer is going to come back. And what was really exciting is it's not just the tumor that he was looking at, it's kind of the whole. We have all of this information on the CT scan, so where clinicians currently are only looking at the tumor, but he shows that also in the region surrounding the tumor, even in the areas of the bone marrow, shows like a different kind of uptake that the physician might not be looking at that is indicative that these patients are going to do a lot worse. So kind of he's built a holistic model there, kind of incorporating all that information with some clinical information, demographic information, and really shown that it's outperforming what the clinicians are currently using, which is just baseline cancer stage to predict how well they're going to do.
Amazing. Yeah. So evidence.
Absolutely.
Right?
Definitely.
To prove that it works.
Exactly. Yeah. So it's not just like, can we validate it on other data sets, but it's also showing, can we improve what the current clinical standard is? Because if we can build this model gives us, say, an 80% accuracy, but the clinicians already have an 80% accuracy, then it's not really adding anything to their workflow. So we kind of want to show that it's going above and beyond what the current clinical standard is to show that there is some clinical utility in it.
Yeah, there's potential.
Absolutely.
Definitely, yeah. How does this connect to the work with the neck?
Absolutely. So we also had another PhD student who recently graduated last year, Dr. Tricia Chinnery, who worked on this project, really trying to personalize treatment for head and neck cancers, so specifically oropharynx cancers.
What is that cancer?
Cancers at the back of the throat. They're at the back of the throat or the back of the tongue. So these patients usually get treated with chemo and radiation together. And you can imagine with the head and neck, when you treat it with radiation, there's a lot of sensitive organs around there. Yeah. So you got your salivary glands, all the swallowing functions and that sort of thing. So these patients get quite bad side effects in terms of trouble swallowing, dry mouth. So it can be quite debilitating for these patients to go through this treatment. So we've also used a radiomic approach here where we look at scans that they're already getting taken as part of the radiotherapy workflow, pull out radiomic features that the physician might not be looking at. And we also incorporated, because we have them, is information about the radiation treatment plan. So how much dose is each region getting, or how much radiation, to make a holistic model to predict kind of the side effects, and also how the tumor is responding to treatment. So in a lot of these cases, the tumors are quite large. So halfway through treatment, they might shrink quite a bit. So what they would do is they would replan the treatment halfway through treatment. Okay. And really that's to save some of those side effects, because you don't want to be treating a very, very large region once the tumor has shrunk. So so there's a lot of different applications that we can use it, and we've shown good results in that area so far.
Yeah. Does this connect to the work that Dr. David Palma is doing with SABR?
Exactly.
With the SABR radiation? Yeah.
Yeah, so we haven't done anything with SABR specifically in the head and neck or with that surgical project, but we do have another project that we're working on that's using SABR to treat multiple lesions in the lung. So this actually, I had a graduate student who just defended his PhD last week. So Dr. Edward Wang just completed as part of the MD PhD program here at Schulich. And what he was trying to do was optimize the radiation planning for these patients receiving SABR treatment. So a lot of these patients were patients that Dr. Palma had treated. Most of them have many, many lesions in the lung, or many tumors in the lung. So it could be 3, 5, even up to 10 tumors spread throughout the lung. And to plan the radiation, you can imagine we have all these different spots that we want to treat. It gets quite complex in terms of planning and how we can optimize that treatment. So at our cancer center, it takes about 8 7.5, 8 hours on average to plan one of these treatments. But Edward developed an AI model to do this very fast, and that the physician can just type in a number, press go, and it'll create the dose or the radiation treatment plan. And it allows them really to look and see, is it safe to deliver? Can we actually deliver this? What is the best dose that the patient should be receiving for these lesions? So it's really allowing to get right into the clinical workflow. And he's actually put that tool right into one of the systems that they're using in the clinic. He's tested it with a bunch of physicians. So that's really kind of on the translational pipeline, which is really exciting.
Yeah, that must be so exciting.
Yeah.
What took, 8 hours?
Yes.
Is now
Yes, a click of a button, 10 seconds or so to get it all populated and presented. So,
right. Yeah. The translational aspect of your work, I think is very important and also fascinating. I know, like most people, you do have a personal connection to cancer with some family members.
Absolutely. Yeah.
I believe your father and your grandfather.
Yes, correct. Yeah.
Very, very sorry to hear that.
Thank you.
My father also. So I know that, does that inspire your work?
It does.
If we step away from the radiomics and AI,
exactly.
Is that what kind of gets you to the lab every day?
Yeah, 100%. Yeah. And I think it's been throughout my whole journey, kind of both in high school when my grandfather was first diagnosed with lung cancer, to my undergraduate degree when my father was diagnosed with colorectal cancer, who had a long battle with colorectal cancer, and who eventually passed away while I was doing my postdoc before coming here. And then my grandmother as well with pancreatic cancer. So it's kind of those experiences and seeing those loved ones have to go through that, and not just one type of cancer, but looking at 3 different types of cancer. So those 3 really are the motivation of why I do what I do, to kind of improve care for future patients going forward. Whether that little bit of impact that I could have, I think is truly why I do what I do. Yeah,
oh, definitely. That is a common theme when I have the privilege of meeting cancer researchers, oncologists, imaging scientists.
Yes.
There's a through line of a deep empathy and personal experience in combination, right, with wanting to do that. And I think, is it fair to say that, cancer research and treatment, you get to see that maybe more than in any other scientific field?
Absolutely. Yeah, I think so. I think there's always that personal connection. And then I think for me also too, kind of on a day-to-day basis, my lab is physically located at the Frisbeaton Family Cancer Center. So I see the patients every day when I walk into work. So again, another motivating factor kind of to know why we're doing what we're doing is so important to help these patients. And I think that's really big, specifically in the cancer research field, definitely.
Right. Yeah, we always hear location.
Absolutely.
Location in real estate.
Exactly.
But it also plays a role in your work, right?
It does, absolutely.
Why is it so important, or why are you lucky to have your research facilities so close to the clinic?
Yeah, I think that's a huge important factor for our research specifically, because we're working on this translational research. Being actually physically located in the cancer center, not only do we see those patients on a day-to-day basis, but we get to interact with the clinicians and all of the healthcare staff regularly. We see them regularly. And I think that's the key, is that clinician interaction. So I have a clinician, Dr. Pensilla Lang, who's a radiation oncologist, whose office is right next to mine.
What's her name, sorry?
Dr. Pensilla Lang.
Oh, right, yes.
So her office is right next door. She's within our lab space, so I interact with her on a daily basis, and that's how we can kind of come up with new ideas, where she may come back with a clinical question that she saw in clinic or something like that, or she has new ideas that she's been seeing on the basis of her day, that we can really use some of our tools to apply. And then the same goes with all the other radiation oncologists, medical oncologists, surgeons that we kind of can see on a very regular basis being physically located there. So it really helps us in terms of getting those ideas and what we should be working on, because we want to be working on clinically important things that really come from the clinicians. So being physically there, seeing them, interacting with them, being able to meet with them regularly because they're right next door makes a huge difference.
Yeah, that's almost a great argument for collaboration in physical proximity.
Absolutely.
I know COVID took that away from a lot of fields of work.
Absolutely.
A lot of people miss those opportunities to run into a colleague in the hallway and talk. And I know a lot of probably some of the best ideas come out of those interactions.
Absolutely.
Would you say that's true?
100%. I agree. Yeah, that's where really all of our ideas have come from, is those close interactions, or being able to see these clinicians on a regular basis and running into them in the hall, or running into them at a meeting or something like that, because I think that's where our ideas come from. And that face-to-face is so important to be able to kind of come up with those new ideas, find out what's really the needs are in the clinical workflow right now that we can to help solve. So being co-located and physically within the Cancer Center, and specifically in the Gerald C. Bain Center for Translational Cancer Research, which is really the goal of that center, is to put clinicians and researchers together, has really helped tremendously in terms of developing our research program from the ground up. So it's been really fantastic.
Okay. Can you talk a little bit more about that, the center?
Yeah. So the Gerald C. Bain Center for Translational Cancer Research is at the Verspeeten Family Cancer Center. And really, it incorporates not only our imaging program, where we kind of have clinicians and scientists come together, but also clinical trials, radiochemistry, biospecimens, and that sort of thing. So it kind of brings together all different areas of cancer research, with the overall goal is to translate a lot of this work. So working closely with clinicians, clinical trials, so how we can kind of incorporate research into the clinical workflow and develop those paths moving forward. But really, also the co-location has been a huge part of that to kind of advance research and new ideas.
Right. I know a lot of the colleagues that you're talking about that you get to work with. When I have the pleasure of meeting with them and talking with them, one theme always comes up, and that's Schulich is just known for its imaging.
Yes.
And I know imaging, I guess, first of all, how important is imaging in cancer diagnosis and cancer treatment?
It's crucial. I think it's one of the main factors and products of the diagnosis and the staging process. Because I think if we didn't have imaging, we'd never actually be able to see what was going on inside the body, kind of being able to visualize that tumor, has it spread to other locations. It really gives us that localization information that we wouldn't get with a blood test or something like that. So being able to kind of get that glimpse inside the body of what's going on and how big is the cancer, has it spread, is really so important in terms of determining, well, how aggressive it is, how large it is, and then what's the optimal treatment. So it plays such an important role, not only into the diagnosis and staging, but also in planning treatment. For example, for radiation therapy, we need imaging to be able to plan where the radiation is going to go, how much radiation is the tumor going to get versus healthy tissues, and then follow up as well. It's not just kind of at the beginning, it's at the later stages. So is it working? Is the cancer shrinking? As those spots that maybe have metastasized, they're getting smaller? So it definitely plays a major role in all aspects.
Yeah, can't understate the role of imaging.
Absolutely.
Why do you think Schulich has this reputation? Because it's Canadian-wide, but it's also worldwide. You know, I've spoken to some oncologists from the States, one from Europe. Right. They even know this is true. What has led to this reputation?
I think we just have such a strong imaging program here at Schulich. So not only at the Cancer Center, but specifically at the Robarts Research Institute at St. Joseph's Hospital. I think there's so many different imaging research programs that are just making groundbreaking research and in different areas. And it's not just cancer. I think it's kind of a whole field, neuroscience as well. So I think it's just all of those different expertise have come together across multiple different sites across London and just are advancing it in so many different ways. I think we have such a strong imaging program with so many different specialties and areas of expertise that we're just kind of moving the field forward in so many different aspects, not just cancer.
Yeah, and it's definitely a destination for that research that requires imaging.
Definitely, yeah.
When you were a younger student and you were thinking about your career trajectory, did you know that imaging would be something that you would be interested in?
Yeah, it wasn't really until I did a degree in radiation therapy where I kind of first really got firsthand insight in terms of the impact imaging can have in terms of treatment and of these patients. So I think at that point, I didn't really know where I was going to go. And I think I feel so fortunate to have kind of been in now the imaging field since as a grad student. I think that's where I first was really introduced to how we can use images more, how we can pull more information from images. And that's just kind of built throughout my career now. So I feel very fortunate to have had the opportunity in graduate school to kind of get my feet wet in that area and then kind of build it from there.
Yeah. When you started, would you have thought you would be at a place where, you know, a clinician can, again, press that, input some data, press a button, get the information that would have taken a day or two
Absolutely.
before?
Yeah, no, I definitely didn't think so. Because I think, so when I started my graduate school, we're first dabbling in this area in terms of pulling out information, but we were using very small numbers of features, like 10 features, a very basic machine learning model.
When looking at
an image. Yeah. So to kind of think where the field has come, even in the last 10 years, 15 years, it's been amazing to see what we've been able to accomplish and how much information we're going to be able to get out of these images, and just how we can use them and how we can apply different AI models. I just think it's been fascinating to watch the field grow. It's been really growing at a tremendous pace, I'd say, over the last 5 years or so in terms of where we're going with AI and applications of AI. So it's going to be interesting to see kind of where that carries forward over the next 10 years.
Yeah. Well, what's your prediction?
Yeah.
Here we are. I feel like 2025, they're going to identify this year.
Yeah.
2025 as the year of the explosion.
Absolutely.
Whatever you wanted, the revolution.
Absolutely.
Where are we going?
Yeah. And I think that's a great question. And I think AI is going to play such an important role, kind of focusing on the clinical aspect and kind of clinical workflow and research. But kind of where it's going long term, I think we still are going to need that buy-in from clinicians, because I think we can get all this data and build all these models, but we need to make sure, we're looking at a clinically relevant question, that the physicians are going to use what we're building. So we could have big AI machines plow through all this data, but if it's still, we kind of lose that human aspect. So I think there's always going to be that need for that human interface with the clinicians and kind of how we can use it going forward. But I just think how we can process the data, it's just everything's growing so much. How much data we can process is growing. So I'm really excited to see where it goes, because I think there's so much opportunity out there in terms of where the field is going to advance. So,
right.
Yeah.
So what I'm kind of hearing is, all the AI, all the computers, supercomputers, massive data sets, it's great.
Yeah.
But if you don't have the human buy-in,
absolutely,
it's not gonna translate.
Exactly. I agree. Because I'm never in this field, never to replace like a physician or anything like that. And I think that's the key, is how we can best use AI. And I think we all need to think about that going forward in terms of how we can best use it, not only in our day-to-day lives, but specifically in our research, to get the most out of it and kind of to help in different aspects of research or and that sort of thing to see, because I think it's going to be interesting to see how it goes over the next few years.
Right. Well, what is the danger of maybe using AI incorrectly? Would it be causing more work?
Could be.
On the clinical end, or is there, do you see some of the
I guess it's just, I think you never sometimes know what you might get, and do we actually trust the answers coming out of AI? What is really understanding what it's doing almost behind the scenes or in that black box, especially when it comes to clinical care and patients' outcomes, because the patients really are the most important at the end. So if you don't kind of have a sense of what's going on, you don't know really why it's saying what it's saying, if the predictions are correct and that sort of thing.
The hallucinations
exactly.
It can have,
So I think, there's always that human aspect that we're going to need to be able to kind of work together and use
to balance it.
Yeah, absolutely.
Have you, when you go to conferences or you get next year's conference themes, do you find that there's a lot of AI happening?
Definitely, yeah. I think every year the field of AI in terms of our research area is just growing and growing in terms of the number of abstracts or presentations that you see on AI, and different applications in terms of different disease sites, different imaging modalities, things that we haven't even thought of in terms of how it can be applied to different aspects of imaging. So not only to predict outcomes, but how we make make the images better in terms of quality and that sort of thing. So I think it continues to improve. I think really the bottleneck right now is the actual translation in terms of moving those tools from the labs into the clinic. Because I think all the manuscripts and papers that you read are great models that have been developed on large data sets and that sort of thing. But actually getting them to move into the clinic, I think that's where we're kind of at a bottleneck right now in this field, that we need to kind of focus on that translational aspect to kind of see how they can actually be used.
Yeah. Bottleneck's a great way to kind of get all this research, all these, labs all over the world doing this amazing work.
Yeah.
But there's only so much that can get out
Absolutely.
and actually make an impact.
Exactly. Yeah. So it's not just, is it relevant? Like, are the clinicians going to use it? But how are they going to use it? Are they going to actually change their minds and that sort of thing? So I'm really hoping the field will kind of move in that direction to say, okay, well, we built these models, let's validate them and say, like, yes, if they work on our data, do they work on data from another center? But then how do we get that into clinic? Whether that's doing some sort of observer study to see, well, how are the clinicians going to use it? Putting these models maybe into prospective clinical trials to see if we're already doing these trials, like if we tag on this AI model to see in the background kind of what's going on, because I think a lot of the models stop at that development stage and they don't actually get over to the next step. So it'd be great to see more models kind of moving into that clinic and clinical translation and seeing how we can best use them to benefit patients.
Yeah, I think that's a really great point. If you have a clinical trial, and I think you said, can you tag it on?
Yeah, exactly. Yeah,
because it's not doing anything to the patient, right? It's just working in the background, humming away.
Exactly.
Is that easy to do, or how do you do that? How do you say, okay, we're doing a clinical trial, but let's add some AI research to that and see how that works?
For sure. So I think the first step is, like you said, we just kind of leave it in the background, right? We put it in there, but we can see now we're testing on patients that are coming through the clinic prospectively, like these new patients coming through, because most of the models we develop on patients that data has been collected over several years before. So it's kind of giving us a new data set to look at. And then you kind of just leave it in the background to see what it's doing. That could be the first step. You don't even need to show it to the physician or the clinician or the patients, just to see, well, is it still working on this data that we've collected? And then if we can say, yes, look, it tested it on these maybe 20 patients in a clinical trial, it's doing quite well, and then kind of figure out, well, the next step is how we can incorporate that into the decision making. But there's so many different aspects along the way to get it from point A to point B.
No, again, it's something I've learned in this journey doing the Catalysts podcast is just how much work goes behind the scenes, getting research into the hands of the right readers, and then taking it step by step into the clinic. It's a lot of work.
It is a lot of work, yes. But we're excited, and hopefully we'll get there soon.
I know you're expecting.
I am, yes.
In October.
October, yes.
Congratulations.
Thank you.
Yeah.
Thank you.
There's something about bringing a baby into the world really makes you think of the future.
Yeah.
Do you think, or how do you think of the future when you think of your new arrival?
Exactly.
How cancer is going to be in their lives? Because I think it's, the number one killer in Canada, and I think in most of the world. It's overtaken heart disease. But obviously this technology keeps coming, and the revolution is happening in 2025.
Yeah.
What relationship do you think your child will have?
Yeah, that's a great question, because I think thinking about just not even from like where the field of cancer research and that sort of thing going, I'm hoping we can continue to make advances and get, by the time this generation is kind of growing up and that sort of thing, that we've developed these tools and developed more personalized approaches to kind of personalize cancer care more than it currently is now. And I'm hoping that's where that field is going to go. But then there's also the whole AI side of things as well, in terms of what impact that's going to have going forward as well. So it's going to be an interesting time. I think it's a different generation now, and even every generation is kind of, there's so many changes and that sort of thing. So it'll be interesting to see as my two kids grow up how things are going to change. But I'm hoping we're kind of continue to move this field forward, kind of can advance patient care and clinical care for these patients to really provide personalized treatment, and hopefully improving outcomes continuously year after year to try to get the outcomes better, so we don't have such a negative impact in terms of the impact of cancer in our country.
Right. And I know imaging is going to play a vital role in this.
Absolutely. Yeah. And I think that's going to be key is how we can use this imaging kind of as we advance imaging, not only the quality of the images that we're taking, but what information we can get from them. And I'm hoping to see that by the time they grow up, that's kind of going to be incorporated into the clinical workflow in terms of how we can use all of this data and information that we have to the best of our ability.
Yeah, great. Yeah. Well, I wish you all the luck
in
the world getting the bottleneck
solved.
I think that's probably one of the biggest things we have to do.
Agreed, yeah.
Yeah. And I think, on behalf of everyone here, just thank you for your work. Cancer research, treatment options is definitely, something that we all will face in our lives. So we do appreciate you and your work.
Oh, thank you. And thank you for having me.
Yeah, great. Thanks for being here.
We hope you enjoyed this episode of The Catalysts, a medical science and discovery podcast by the Schulich School of Medicine and Dentistry at Western University, Canada, bringing you exclusive conversations with leading scientists and researchers.